All right, let me share screen. Okay, cool. All right, so question one, sorry, 1 second. 1 second. Okay, question one is telling us that a biotech company has isolated a programmable DNA endonuclease they believe may be the next big thing. And then experiments reveal that a 0.2 nanomolar target DNA duplex at that value, about 75% of the protein is bound to DNA. And to assume that the protein concentration is much lower than that of DNA, what is the value of KD? So the way we could go about this is using the fraction bound formula, which is the fraction bound is equal to the concentration of ligand divided by ligand plus the dissociation constant. And then solving for the dissociation constant, we get this formula over here. And if we just plug in our values, we can solve. So KD will end up being equal to 0.2 nanomolar, because that's the ligand concentration given, over 0.75, which is the fraction bound, minus 0.2 nanomolar. And that will end up giving us 0.07 nanomolar. So this next question is a bit more involved. So you're designing mouse-based drug trials for the inhibition of an oncogenic kinase by the experimental compound DES9 developed at your startup. DES9 has a molecular weight of 559 grams per mole and binds its target with a dissociation constant of 0.5 nanomolar. You are initially testing the drug in mice, which have a blood volume of 2 milliliters, ignoring any issues of drug clearance, etc. How much DES9 would be required for 91% and 99% inhibition? So the first thing we're going to do is calculate the concentration of DES9 required for 91% or 99% inhibition. And I'm going to do this question just on 91%, and you could easily just change the values to do 99% inhibition as well. So again, we could solve the concentration using the fraction bound formula. So F equals L over L plus KD. Solving for L, you get F KD over 1 minus F. And then for the case of 91% inhibition, we get that the concentration of DES9 is equal to 0.91 times 0.5 nanomolar over 1 minus F, which is just 0.09. And then this equates to 5 nanomolars. So going on from that, the reason we wanted to calculate concentration is because you could relate this to the mass. So if you recall, the concentration of something is equal to the moles over volume, and moles could be found by doing mass divided by the molecular weight of that molecule, and then just all over V. And then solving for mass will give us mass equals concentration times volume times molecular weight. So we have the concentration as 5 nanomolars, and I'm going to put it into scientific notation. So 5 to the minus 9 moles over liter. The volume is 2 milliliters, which is 0.002 liters. And then the molecular weight is 559 grams per mole. And these two values over here are given. And then I'm going to use significant figures, so you end up getting 10 nanograms. And then again, you could do this, you could repeat this with 99%, except these values would change over here. All right, the next question. Shown below is a binding isotherm for an enzyme called the phosphatase in a potential drug or lead compound known as JF99. There's a tryptophan near the binding site, and the fluorescence from this residue increases upon binding the compound. You'd like to estimate the value of KD from this plot. Is this reasonable? If so, what is the value of KD? So the fraction bound equation tells us that if L equals KD, then F equals the fraction bound is equal to 1/2. So if we look at the fraction bound versus L graph, we can determine KD by going to 0.5 and then going down. But the thing is, this only works if you have a steady maximal value, like over here. So if we look at the graph given, we can see that this is not steady. It looks like it's continuing to increase, and therefore we cannot use this to calculate KD. So you would say no, because it's not saturated. Okay. The next question says, now suppose that you increase the concentration of JF99 to 1 micromolar and find the changes in the fluorescence signal reach roughly 500 units and the signal doesn't appear to dramatically increase. So since it states that the signal does not increase anymore, we can assume that we have a steady maximal value and we are at saturation. So therefore, we actually can figure out the KD value. So if we look at this graph and we draw a line up until, let's say 500, let's say this is 500, half of 500 would be 250, and that's our F equals 1/2 value. So we go over and we go down and we get 20 nanomolar. So that will be our KD. And then what is the value of delta G bind? So that could be found by just using this relationship. So, you know, R is 8.314 joules per mole Kelvin. T would be in Kelvin, it would be 310 Kelvin. And then natural log of 20 nanomolars. And then that equates to negative 45.7 kilojoules per mole. And finally, the next question is asking, what is the fraction of unbound protein? So F unbound is just equal to 1 minus F bound. So it's going to be equal 1 minus L over L plus KD. And then if we just plug in these values, we could find the answer. And then KD we found was 20 nanomolar. And just make sure everything is in the same units. So the ligand concentration they gave us was in micromolar and our KD is in nanomolar. So just convert everything to molar. So you could find the right answer. So you get 1 minus 0.98. So your fraction unbound would be 2%. And that's all for all these questions. Does anybody have any questions? Okay.
Okay. Share my screen. Okay, so I'll be presenting on question 2 of problem set 12. And so the question is asking, it gives you a binding isotherm and it's asking, the protein has 2 binding sites for the ligand. What are the values of the KDs for each binding site? And to show how you can determine this using the graph. And so what you want to notice first is that there's 3 distinct regions. And so for this of the graph curve, and for this portion, we're going to be using the first and the last. And so in order to determine the KDs, you need to find the portion where the line extending from this first region and this third region would cross through the x-axis. So I did this by just kind of drawing lines, like projecting the lines outward from where they are. And it doesn't need to be exact because you'll get like a pretty good estimate. And then drawing a value through the x-axis. And then you can see that for this portion, it's at about -2. And then for this portion, it's at 1. And so if you use this formula, it can kind of help you figure out why like we're taking these values. But so you know that the log of KD1 will equal about 1 and log of KD2 will equal about -2. And then from there, you can use just logarithmic properties to determine the values of the KD1 and the KD2. And then for the second portion of the question, it's asking whether the protein is exhibiting positive or negative cooperativity. So first, we kind of want to figure out, define what cooperativity is. And so the textbook defines it as the extent of binding increases more sharply than for a normal binding isotherm as the concentration of the ligand increases. And so basically, you can just think of it as like the ligand molecules are cooperating with each other to make binding stronger. And so for positive cooperativity, the two ligands are cooperating to increase interactions with the protein. And then for negative cooperativity, it's kind of the opposite. The ligands make it more difficult for each other to bind. And this is kind of like a picture showing you like what that would look like, sort of. And so what we need to remember is that if the first dissociation constant is greater than the second, that'll be positive cooperativity. And if the first is less than the second, it'll be negative cooperativity. And this makes sense because small dissociation constant indicates more tightly bound interaction. So you can use the values that you determined in the first part of the question, which were, I think, 10 and, you can use the values from the first part and plug them into this equation. You can pretty easily get the answer. And then make sure to explain why. And then the third portion of the question is asking about the value of the Hill coefficient. And basically you need to solve for it two different ways. So using the graph on the diagram and then using also the formula for the Hill coefficient. And so the Hill coefficient is the steepness of the log-log binding isotherm. So this binding isotherm at the point when the protein is half saturated with ligand. And so this will be kind of like show up in the second portion of the curve, the like middle portion of the straight line here. And so the easiest way to find this is you can just actually take the slope of the line. So you can see here over 1 of 2. So the slope of the line is about 2. And then you can also use this equation, 2 divided by 1 plus the square root of KD2 divided by KD1. And so you remember that KD1 was 10 and KD2 is 0.01. So this will give you a pretty small number once you square root it. And so again, you get that it's about 2. That's just approximately. And then the last portion of the question is just asking what's the physical meaning of the Hill coefficient. So I feel like the Hill coefficient, like you can see it's pretty easy to solve. Like if you're just either using a slope or using even the equation, but it's also important to like understand what it means for like practical use. So yeah, it's pretty easy to calculate or observe, but it's not as easy to understand. But some ways that I think you can think about it is that it's a measure of the extent of cooperativity in a binding process. So like the degree of cooperativity, how cooperative is it? And it also kind of is how physically connected the two sites are, which determines the degree of cooperativity. So I should say cooperativity, but yeah. Okay, that is the whole question. Does anyone have any questions or want me to repeat anything? Okay, cool. Pass it on to the next tutor.
All right, I'm going to start with question 3 then. Share screen. Okay, so for question 3, we're studying a dimeric protein that displays negative cooperativity, and we're asked to make some inferences from the two theoretical isotherms we're given here. Before I get started, I want to also point out that if you want a more detailed discussion of this and the previous question subject matter, that would be in chapter 14, section 15 of the textbook. But moving on to the first part of the question, we're asked to label the tense-like and relaxed-like isotherm and show how we determine the values of the two KDs. So I'm going to start with determining the values of the two KDs. We proceed pretty much exactly like the previous problem. We start with this expression, and we note that the log of ligand concentration is equal to the log of KD. So on this graph here, we can separate each of the individual ideal isotherms and look at the point at which they intersect 0 on the y-axis here. So that would be this point here and this point here. And we know that the log concentration here corresponds to the log of the KD. So the KD corresponding to this point, for example, is about 10 to the third micromolar. And for here, it's about 10 to the negative third micromolar. And then we want to determine which KD each corresponds to. And for that, again, we note that the protein displays negative cooperativity. So as discussed in the previous portion, that means that KD1 is less than KD2, which means that we know this corresponds to KD1 and this corresponds to KD2. And based on that and the information given in the question, we know that KD1 corresponds to the relaxed-like isotherm and KD2 corresponds to the tense-like. So we can also label those as shown. For the second part of this question, we're asked to derive an expression for the ligand concentration where the protein is half saturated. And the key thing to start off with here is to note that this ratio of fraction bound to unbound should be equal to 1 at the half saturation point. So from simply rearranging this, we get that the ligand concentration over KD1 plus ligand concentration squared over KD1, KD2, and that's just this expression multiplied out is equal to 1 plus the ligand concentration over KD1. We can cancel this expression out from both sides, and when we multiply across, we should get a formula for the ligand concentration, which is the square root of the product of the two KDs. And then using this and the KD values we derived in this section, you should be able to find the ligand concentration at which the proteins have saturated just by plugging in values. And then for part 3, we need to indicate the point of half saturation on the graph above and sketch the shape of the isotherm based on that. So we get the concentration at half saturation from the second part of the question. If we just take the log of that, we'll get the x coordinate for the half saturation point, and we know that the y coordinate is 0 again. So we can plot that point, and then let's assume, for example, that the point is somewhere here. Just for the sake of it, you'll of course have to calculate this out yourself and see, but this is just for the sake of example. We know that since the isotherm displays negative cooperativity, the curve starts here and should look roughly like that, where it's, sorry about that. 1 second, there we go. Where it starts off following the slope of this line, and then curves over to this line, passing through the half saturation point. And that should be all for this question. Are there any questions?
Okay, so I am presenting next. I'm going to apologize in advance for the scarcity of my slide, as I typically present with third grade and did not have very much time to present something particularly exciting looking. However, I will do my best to help explain this problem, and if you need any, please ask questions, because that will really help guide me in terms of what kind of answers you guys are looking for in terms of what you need to answer this question. So for question 4, it presents a series of Lineweaver-Burke plots, and it asks you to label them according to the names that you guys learned in class. Those names being the substrate dependent non-competitive, competitive, and reversible non-competitive. And the important thing to recognize here is that the x-intercept is going to correspond to the -1 over km value, and the y-intercept is going to correspond to the -1 over Vmax value. So you can see when you look at the lines, you can see what is changing both in terms of km and or Vmax by comparing the red and the blue line, and you should be able to match up the actual name of the type of inhibition that you're seeing and the actual graph that you're looking at. If you have any questions, please feel free to ask me more either in chat or interrupt me at any time. For the second question, it asks about Km and Kd. So they're very different parameters and derived from different models, and it asks under what conditions they are very similar. So if you look at what Km and Kd look like, Km is defined as kind of being the rates of things leaving the enzyme substrate interaction. So K -1 plus K2 over the actual rate of things entering the enzyme substrate complex, which would be K1. So if you look at that and then compare it to the actual equation that you would use for the dissociation constant, that would be the K -1 over K1. And you can see by playing with the actual reaction rate, you can make the equations appear to be very similar. And then for the next question, it asks about an enzyme accelerating a reaction by a factor of 10 to the 11. And it tells you that the effect of the enzyme is solely due to the change in energy of the transition state. So in this question, it's important to recognize what they are giving you. So they're giving you RT, and they're telling you something significant about the actual energy of the transition state. So it's important to try to think about what equations you guys know and how that would relate to how you would answer this question. So I'm going to say that, like, when I look at this question, I do see like the Arrhenius question, like equation would appear to apply to this actual question. And it doesn't give me anything about A though, right? Because the Arrhenius question would be K time, like K equals, the rate equals A times E to the like actual activation energy over RT, negative activation over RT. And in that equation, you have A, but it's important to recognize that they're only asking about a change in the energy of the transition state. So you can assume that the A value for that equation would be the same for both systems. And yeah, if you have any questions about that, feel free to ask me. I'm sorry that I don't have slides that would make what I'm saying a bit more clear. But yeah.
Okay, I will start question 5. There are no questions for Tyler. All right. You should be able to see my clipboard now. So question 5 is another example of a Lineweaver-Burke plot, but this time you're doing some numerical calculations with it. You are, so to, as a refresher, the Lineweaver-Burke plot is used to determine values in this equation, in this linear equation, where the y-intercept will be 1 over v max and the slope will be km over v max. And looking at the graph given in the homework, you should see in the inset, they have zoomed in onto the y-intercept, and you should be able to see that 1 over v max will be equal to 2, which means that v max is equal to 1/2, and the units for that would be per second. And then from here, you are given data on the right side of the graph where you're told 1 over v naught, and 1 over v naught here would be just this 1 over v. So plugging any pair of values into that, you should be able to have two equations that are end up subtracting. So you'll have 1 over v 2 minus 1 over 1 over v1 is equal to k over v max. You'll just get a relation like this where the y-intercept is no longer there, and you'll be able to figure out the slope from this, or km over v max from this. And when you find km over v max, you already know what v max is, and you could just solve for km. And then you can do this for the no drug case and drug Y case. For part B, they ask you about what the mechanism corresponding to drug Y. And as you should have been able to see from above, this one matches the case where V max does not change, and you should be able to figure out from that. So yes, V max does not change. And then the last question talks about the inhibitory constant Ki. I believe the formula was in lecture, but I will show you a quick derivation of it, starting from Vmax. So Vmax is defined as Kcat times the total enzyme, total concentration of enzyme. So for our classic ESP model, you have that the E total would be equal to ES, or E plus ES concentrations. But when you add in an inhibitor, this inhibitor also interacts with the enzyme to give you an equation like this, where it's enzyme plus I, the inhibitor. And then that forms a complex EI. So this EI will be, you have to consider this EI when you're going to consider E total. So now the E total for this reaction would be E plus ES plus EI. And then EI can be similarly defined as in ES, where EI will be equal to the concentration of E times the concentration of I over Ki. And then from here, you plug it back into the equation for your velocity, which is V equals V max S over Km over E total. And from there, you should, if you plug in the E total from this one and take the reciprocal and then go through the calculations, you will find that Km star here, which is the Km for this inhibited drug or inhibited reaction, would equal to Km 1 plus I over Ki. And here I is equal to 3 micromolar, and you should have found this Km from the no drug condition in part A, and you will be solving for Ki. And this Km star is from the drug condition in part A. And that should be all for question 5. Are there any questions? Sorry.
Okay, should I end the recording for this session? I'm not sure if you guys have any questions, but I will stick around for my question at least, because I know that, you know, given that I didn't have very many slides, it may have not been the most thorough explanation, but I will stick around for a little bit. Okay.